All right, so this presentation is to help with two proportion Z intervals and two proportion Z tests for AP Statistics. All right, so a couple quick reminders. Remember, all confidence intervals have the same general form, and this is on your formula sheet: estimate plus or minus critical value times the standard deviation. And all significance tests have the same form: estimate minus the hypothesized value over the standard error, standard deviation. Remember, the hypothesized value is your null hypothesis that you believe to be true until you're proven wrong. Now, what we want to do is we want to be able to find the difference, or estimate at least the difference, between proportions within a population. However, in order to do that, we need to know how to do the difference in sample proportions. So that's why we're going to actually take a look at sampling distributions of the difference of two proportions. Now, remember, shape for a confidence interval, proportion confidence interval, remember previously we checked for normality by doing n times p hat and n times 1 minus p hat being greater than or equal to 10. That was checking if our sample size was large enough to say approximate normality. Now, however, we have two different samples, so we need to actually check both. So I need to actually check my first sample size and whether it meets this condition, and then I need to check it for my second sample as well, to check if it meets this condition. Notice if I'm doing a confidence interval that I'm plugging p hat into this condition rather than a hypothesized value. Confidence intervals, you do not start with a hypothesized value, so p hat is all you have to work with. Now, when you take multiple samples, a lot of times it's harder to get a bunch of people in your study because you're splitting them up to begin with. So we typically are okay if this is at least 5. Still, the larger the better, but we tend to be okay with approximate normality as long as they're all greater than or equal to 5. All right, now remember our one sample inference formulas are on our formula sheet. Now we're going to actually shift gears to our two sample standard deviation formulas, which are on the back of your formula sheet. And specifically, we're going to focus on proportions right now. Once again, please note, these formulas for your standard deviation of the difference of sample proportions is on your sheet that you do not need to memorize. Remember, once again, you do not need to memorize these formulas. You need to know where they are on your formula sheet and when to use them, but you do not need to memorize them. All right. So remember previously, this was the general form of a confidence interval for a one proportion Z interval. I have my estimate of p hat plus or minus Z star, my critical value, times my standard deviation. Notice I'm plugging in p hat into my standard deviation because, once again, I do not have a hypothesized value in a confidence interval. Now it's going to be the same general form, however, it's going to look a little bit more complex. It still has the same pieces of the puzzle though. Now my estimate is not just p hat, but it's the difference in my two sample proportions. And my standard deviation is not just the square root of one sample, it's the square root of my two separate samples distributions combined. Once again, this is on your formula sheet, so don't worry about memorizing it. Now here's an example. It says, we're interested in the long-term effects of preschool programs for poor children. Now in this study, we had two different groups. We had a group of 61 children that represented poor children with no preschool. And then we had a second group of 62 children with the same area, similar backgrounds, who attended preschool as 3- and 4-year-olds. Now what we were interested in was whether or not they needed welfare later on in life. Now notice, our first group, the children that did not attend preschool, had about 80.3% of them needing welfare later on, while our sample of children who did attend preschool had only about 61.3% needing welfare later on. This question's asking us to estimate with 95% confidence the true difference in rates of people who go to preschool needing social services versus those who do not. So we want to compare these two different groups. So step 1, I'm trying to estimate the true difference in proportions between the percent of those who need welfare or social services of those who attend preschool versus those who did not. I'm going to define each of my parameters, and I'm going to clarify which one's which with the subscript. So my P1 in this case is going to be the true proportion of those who did not attend preschool that need social services later in life. And my second group, my P2, is the true proportion of those who did attend preschool and need social services later on in life. Once again, make sure you have your subscripts distinguishing which group is which. Now my conditions. I'm going to do a 2 proportion Z interval, and since it's 2 samples, I need to check each sample separately with each condition. Now, I don't know whether each of these samples is an SRS, so I have to be cautious in my generalizing of the data to the population. Now for normality, once again, I need to check it for both samples separately. So I'm going to check it for my first sample and notice that both my values, NP and N times 1 minus P, are greater than or equal to 10. So that's a good sign. But I need to check it for my other sample as well. And once again, notice a confidence interval. I'm using my p-hats in here because you don't start with any hypothesized values. You're just starting with the sample information. All right, therefore, it's reasonable to say that the 2 sampling distributions are considered approximately normal. Now for independence, there's definitely more than 610 low-income children who did not attend preschool, as well as more than 620 low-income children who do attend preschool. Therefore, it's reasonable to say these individuals in each sample are independent. Now, I don't know how they were selected once again, so that could be an issue here. It's also reasonable to say that the 2 groups do not influence whether the others will need social services later on in life. Now to actually calculate my confidence intervals. Now, to find my standard error, once again, this formula is on your formula sheet. I need to find the standard error of the differences distribution. So I'm going to plug in each of my sample proportions separately along with my sample sizes. And I'm going to get a standard error of 0.0801. Now I can use this in my confidence interval formula. I'm going to find the difference in my samples plus or minus the critical value times the standard error. Now, the difference in my samples was the 80.3% minus the 61.3%. This is a 95% Z interval, so my critical value is 1.96, and I already found my standard error. Now you'll see once this is calculated, I get a interval from 3.3% to 34.7%. Also, a good thing to note here is that they're all positive differences, So we can say that we're 95% confident that the percent needing social services is somewhere between 3.3% and 34.7% lower among those who attend preschool. So I actually noticed that since there's a positive difference between these 2 groups, it does in fact appear preschool might be making a difference. Well, now that brings us to switch gears to significance tests for the differences. Now, please pay attention and make note of some of the key points that I'm going to make throughout the significance test and how they're different than the confidence intervals. Significance tests help us decide if the effect we see in the samples is really there in the populations. Now, remember, we can never be 100% positive, but we can be confident in our evidence. Now, we are typically going to start 2 proportion Z tests by assuming the 2 proportions are equal, meaning there's no difference between the 2 groups. The alternative hypothesis, however, is going to say what kind of difference we actually think there might be. So we're going to look at this example. It says cholesterol and heart attacks. And the purpose of this study was to determine if a drug was really, in fact, reducing heart attacks. I don't want to give a drug to patients if it hasn't been found to significantly improve results. So the subjects we looked at were middle-aged men because they are the group that is most severely affected by heart attacks. I had 2 treatment groups, or I had 1 treatment group, 1 control group. My treatment group was 2,051 men who took the drug to reduce their cholesterol levels, and my control group was 2,030 men who took a placebo. Now note, they probably didn't know that they were taking a placebo because that would include some bias into these results. Now the proportion who had heart attacks of our treatment group was 2.73%. And the proportion in our placebo group that had heart attacks was 4.14%. Now notice my treatment group is in fact lower, so that's interesting. The question here, though, is do we have significant evidence that this drug is in fact lowering the proportion of heart attacks? And note, we're going to use a significance level of 5%. Now, my first step is my hypotheses, my population, and my parameter. So I'm going to first define my parameters because I need to get those straight before I try and write my hypotheses. Now I'm going to let P1 be the proportion of men who take medication and still experience a heart attack. And P2 is the proportion of men who take a placebo and experience a heart attack, so without the medication. We want to show that the drug reduces heart attacks, so we have a one-sided alternative. I'm going to start by believing that the treatment makes no difference, that the two groups have a similar proportion of heart attacks. And I think actually, though, that my proportion in the treatment group might in fact be lower. I'm thinking the medication helps reduce heart attacks. All right, now to check my conditions, I'm going to do a two-proportion Z-test. I don't know if the samples are necessarily SRSs, but random assignment helps. So I'm going to proceed with caution in making generalizations. Now this is extremely important. Okay, you might want to come back and read or watch this one a couple times because this is a really big important point. To check normality of significance tests, remember, we currently believe the proportions are equal to each other. We believe that until we are proven wrong. I'm holding on to that fact. Therefore, I'm going to use something called P sub C to estimate the true proportion of these two groups to check normality. Once again, because I currently believe the proportions are equal to each other, I'm going to essentially average the two sample proportions, and I'm going to believe that that is the true value of P1 and of P2. Once again, we're only doing this because we are starting with the belief that proportions are equal to each other. All right, so in this case, to find my combined proportion, that's P sub C, my combined proportion, I'm going to take the number of heart attacks in each group plus my sample size of each group. And this is going to get me my combined proportion, my combined p-hat of 3.43%. Now, I am going to use this in my normality condition because, once again, I believe my proportions are equal to each other. So I'm going to check my first sample size against this combined proportion, and then I'm going to check my second sample size against this combined proportion. Now notice, they are all in fact greater than or equal to 10, and so I can say it's reasonable that the two sampling distributions are approximately normal. Once again, I'm only using P combined because this is a significance test. Now for independence, due to random assignment, these two groups of men can be viewed as independent samples. In addition, it's reasonable that there's at least 4,081 men with high cholesterol. Therefore, I'm going to assume these individuals are independent of each other. Please note, if they're related, they're not going to be independent, as well as if they all come from the same area, location-wise, they might have some eating or cultural habits that could make them not necessarily independent. All right, now to my calculations. Once again, we're using P combined because we started with our hypothesis. Now, to get my Z-score, my test statistic in this case, I'm going to use my P combined here, and once again, this is on the formula sheet, versus my two separate sample sizes. Now, in my numerator, I have the difference of my samples. Technically, I have minus the difference of my parameter, but I'd have really a -0 here because once again, I'm assuming there is no difference. Now if I plug in my proportions in this case, my sample sizes, I get a z-score of a -2.47. Now if I sketched my distribution, assuming that the difference, the mean, is 0, I get a z-score at -2.47. Notice I get a very, very small p-value. All right, so what does this mean? Since I have such a small p-value, the results are considered statistically significant for me to reject my null hypothesis at the 1% significance level. So what does this mean? Therefore, I have strong evidence that the drug does in fact reduce the rate of heart attacks. Now, I put together, just as a summary of these two concepts, I put together a table of the difference between intervals and tests, so intervals on the left-hand side, tests on the right-hand side, proportion intervals and tests. And I also separated it into one sample proportions versus two sample proportions. So this is a great thing to jot down if you're at all hazy about when to do what in these cases. So a little review. For a one proportion z interval, I'm going to use my p hat when checking my conditions because I'm not starting with any hypotheses. And when I calculate my interval, it's going to have the following form. Once again, I'm using p hat in my standard deviation because I am not starting with any hypotheses. However, in a one proportion z test, I start by believing mu is equal to a certain proportion. So I use that proportion in my conditions as well as in my standard deviation formula. Now, let's shift to two sample z intervals. So once again, for intervals, I do not start with any belief about my proportion value, so I have to use my sample proportions when checking my conditions, as well as my sample proportions when constructing my interval. However, with a two proportion z test, I start by believing the two samples are equal to each other. So when I check my conditions, I need to use my combined proportion. That's the proportion that, based off of this hypothesis, it would make sense that they're equal to this combined value, or at least close to it. Now notice, when I take two samples, I am okay with my condition only being greater than or equal to 5, but the biggie is noticing that I'm using the combined proportion when checking this condition, not p hat 1, not p hat 2. And when I calculate my z statistic, I'm using my p hat combined in this standard deviation. All right, so I hope that helped kind of clarify the difference between one sample and two sample proportion z intervals and z tests. Please let me know if you have any additional questions and I'd be happy to help.